Good. So my title is Mechanisms and Models for Non-Classical Nonlinearity in Heterogeneous Materials. We've been talking about heterogeneous materials all the time. We've seen examples of nonlinearity. And what I mean with non-classical here is basically in the presentation that Manuel gave, it's this effect with the transients. It's not the step-like shape that is the acoustoelastic effect, for example, which means that the velocity gets faster when you compress something. It is the effect that when you do something to the sample, the velocity usually or the elastic moduli drop, and then you have a transient process. So everything that is connected to transient changes, to temporal effects, is what I would like to be talking about. And it's also the small amplitude side of the deformation story. So what I would like to talk about is structures causing this nonlinearity, some causative processes, so what actually happens or what might happen at these structures. And I would especially like to highlight the role of slip in contrast to compaction and dilation. So what are actually the structures that cause a nonlinearity? When we look at for example, sandstone, people like to work on quartz or sandstone, then we can compare the absolute values of the sound velocity, for example, and we notice that quartz, which is the main ingredient of a sandstone, it has much higher velocity. So we have velocities of about close to 6,000 meters per second, and in sandstone, it's about half of that velocity, even though it is, like, to the vast majority, the same material. And then when we look at the dependence of this sound speed on the pressure, which is the nonlinearity, in fact, quartz, when we compress it from 1 to 200 bars, the velocities change by about 1%. So it is nonlinear, but it is, has a very small nonlinearity. While when you compress a sandstone to that pressure, you can actually double the velocity. So that it depends much more strongly on the external pressure. And the nonlinearity is much, much larger. So what we can conclude from this is, of course, that these nonlinear effects actually occur in a tiny fraction of the volume in between these, in between the grains. So the grains is basically the quartz with the smaller nonlinearity. So all this nonlinearity has to arise from the contacts in between these the grains. So, and that's the so-called bond system. And when you look at a microphotograph of this of a sandstone, for example, you can actually see that in place. You have the rather homogeneous minerals, and then you have the bond system in between where these processes occur. But it can actually be observed more directly than just in a photograph by looking at neutron scattering. So this is an experiment that has been done quite a while ago on a rather homogeneous quartzite. So quartzite is another rock that consists of quartz, but it has a much stronger bond system. So the quartz minerals are differently arranged, differently packed, and it is more homogeneous elastically. So here we have the strain and the applied load on the sample. And here in the graph, we see the connection between those. So we see when we increase the applied load, we kind of linearly increase the strain. So this is a rather linear relation that we observe like macroscopically. And when we look at the neutron scattering, we can actually look how the diffraction pattern of these neutrons change in response to the deformation. So we can see the deformation of the lattice in the quartz minerals, but this is also only sensitive to the quartz minerals, not to the bond system. And we see that this also in the two different lattice orientation, it changes rather linearly. So we see that this rather homogeneous quartzite has like a linear relation within the quartz minerals and also as a whole, as a rock. On the other hand, when this experiment is done in the sandstone, which is macroscopically much more strongly nonlinear, we see that still the quartz minerals they behave in the same way. So this is still the same linear trend. So the deformation inside the minerals is as we expected from the minerals. But the whole rock itself behaves much more nonlinear. So the dependence of the strain on the load is much stronger. And what is even worse is when you release the load, you go back on a different path, so you have a hysteresis effect. And then there's also a temporal component, so when you do that faster or slower, it looks different. So that actually is an in situ confirmation that the nonlinearity in the sandstone is located in the bond system, and all this complexity that we observe is located in the bond system. So what can be processes that happen in the bond system? It is actually holding this, the whole sample together, but it is also responsible for all this complexity that we observe. So the size that we look at is imaged here. And actually, from just looking at the picture, you don't really see whether this is my tooth or whether this is Mont Blanc. So it's scale invariant, the surfaces. So we have structures at basically any size in between these grains. And okay, this is an atomic force microscope image of a glass bead that is often used in experiments on nonlinearity in granular materials. And you see that also on a glass surface, which is, supposed to be very flat and smooth, we have asperities of basically any size down to the very to the atomic level, basically. So we have all the different sizes present there, and when we look at spectra of the asperity size that we observe in between or on minerals, we actually see that this is kind of scale invariant, so we can expect that we have any size of structures. So let's look at one of these contacts within a material. So that might be a small crack, and it might be some inhomogeneity in the material. It might be a contact between two different grains. It doesn't really matter. So when we look a bit closer at this point where the two surfaces of this contact barely touch, this is a bit annoying. So we can simplify that contact to make a rather an understandable model out of it. So we have the two surfaces, and one of the surfaces is basically suspended by a spring, which is the elasticity of the surrounding material that basically holds these two surfaces in place. And then we can look at the forces that actually act on this contact, and we can assume that the background of this material is kind of is elastic. So the force depends on the distance of this spring. When we pull that down, we have a larger force, and when we push it up, we have a negative force. So, but there's a different force that acts on this contact if it is really a very tiny contact that I've shown is present in the material, not everywhere, but we have these contacts, which is molecular forces between these two contacts. And this is, for example, a Lennard-Jones potential between these two contacts, which means that if the contacts are far away, we don't have any force, so they don't notice each other. But when we move closer with these two surfaces, we actually generate some attraction, which is, for example, can be a van der Waals force between the two different sides of the material. So we have a force that pulls these sides together, but when we push them too close to each other, then of course they get in contact and you have repulsion. So you have a force that pushes these two particles away. So now we have different equilibria in this model. We have one where these two contacts are in a distant state. So both forces are small, the elastic force of the background medium and also the attractive force of these two sides of the contact. But come on. So we can also move these points together, and then we are at this point here, where the attractive force is large, but also the elastic force is large. So we have another equilibrium that is stable, and this one was the one where we are far from each other. So now 2 examples where these forces are acting are illustrated here. One that I particularly like is the gecko feet, for example. It has been shown that actually the feet of a gecko and the way it attaches itself to the ceiling, for example, is due to van der Waals bonds forming between the smallest structures on the feet and the material. And that has been demonstrated because actually they can attach to semiconductor, to atomically flat semiconductor surfaces of different polarities. So it is actually the attractive force between the different sides of that contact. But that has also been used to basically model weight and state friction between 2 different materials that are in very close contact and that form chemical bonds or van der Waals bonds if they are in place and which are broken when the materials move. So the structures are probably the smallest ones, and we can have these types of forces. And now it is the question, what happens actually if we move that kind of contact? Because then we might jump from one of the stable states to the other, and we kind of, by moving that part, we change the slope of this elastic force, and we can move this contact between back and forth between the 2 different states. And this is the shape of the potential energy that we see in this contact for a very close contact here, which is this state here. We have a potential that is has a lower energy at in the closed state, and when we move that apart, it has a smaller energy in the open state. So there's a different probability of assuming these 2 states depending on the distance of the contact, and the transition time actually depends on this potential. So when we have a large barrier, the transition time is large. When we have a smaller barrier, like from jumping from here to there, the transition time is shorter. And that's why we can, and this can be used to model different phenomena that we are observing. And this is one of them. Basically, you have the number of close contact in that model by Zaitsev, which is rather stable. But then when you pull the contact apart just for a moment, the number of close contact drops, and then it increases again, and then it drops again and increases. And it can explain some of the observations that we do. We've also used this concept to reproduce resonance experiments. Resonance experiments are done on basically on a cylindrical rock sample that is resonated or that is excited close to its resonance frequency, and the resonance frequency is here, and then we sweep back and forth across the resonance frequency, and we measure the size of or the amplitude of the deformation, and of course it peaks at the resonance frequency, and then this is done for different amplitudes of driving, of oscillation, and we see that when we increase the amplitudes, the frequency decreases, so the material gets softer. And there's lots of other phenomena. For example, when you sweep in that direction to increasing frequency, you walk along this path, or when you sweep downwards, you walk along a different path. It's asymmetric, so we have a steeper curve here than on the other side, and we have this decrease with increasing amplitude. And we've used this concept that I've just introduced with these 2 different equilibria in this closed or in a contact, which has these all the different energies depending on the normal strain to reproduce these resonance experiments. The important thing about these resonance experiments is that when the material actually gets softer, the amplitudes get larger. So there's a feedback loop. So when you damage the sample, you change the elastic properties, which influences the amplitudes, which again influence the nonlinearity or the damage in the material. So you go from the the softening and the frequency shift to the, we start here. So from the dynamic deformation, you open the fractures, you soften the sample, you change the deformation, you open more fractures, and so on. So there's a feedback, there's a coupling between that. And this rather simple concept of this contact can actually reproduce the lots of features of these resonance experiments. For example, the decrease in the resonance frequency, which is the normal observation. We have a difference between the upward and the downward sweep, which is due to the different transition times. And we see the asymmetry, the time dependency and relaxation, which I don't show here. And actually, there's a dependency of the speed with which you do the sweep. When you do the sweep faster, you see something different. When you do the sweep slower, that's just because the adaptation of the rock has more time, and you see some kind of a different behavior. And in principle, the difference between the upward and downward sweep gets smaller when you do the experiment slower, and this can be reproduced here. Good. So the other thing that I wanted to highlight is the role of slip, because here we have these contacts that we bring closer in contact, or we take further apart, and this dynamics is useful, or it's a useful model already to reproduce some of the observations of the nonlinearity. But a particular role is played by the slip. So an experiment that illustrates that really nicely is the atomic force microscope experiment here, where we have this cantilever that is placed on the surface in like an atomically closed distance, so what I mentioned before. And then, yeah, it is pulled across the sample, and the force and the deformation is measured. So now we see a dependency on the force that is needed to pull this the needle, the atomically small needle, to pull it away. That depends actually on the time that this needle has been at rest at that particular location. So there's a slide hold slide experiment, which is often done in when friction is analyzed, but at a very small scale, where these the processes that I introduced in the beginning are at play. So when this experiment is done in a continuous way, then there's, the needle is stopped, and then it's moved again. And if this stopping time is just very small, then the lateral force that is needed to pull this needle apart is very small. But if the time increases, that this needle is at rest, then the force it takes to pull it off again increases. So that is actually a proof that this contact is aging. So that's what the terminology that is used there. And it depends on time, which means that there's some kind of thermodynamic process that forms these bonds across these contacts to the needle. So and that is kind of an analog for the smallest scales contact. I think that we have in rocks, showing that there's a time dependency and illustrating a mechanism for it, because here you can investigate it a bit closer. What is the purpose for that? For example, by purifying the surface, or also by doing these experiments in vacuum or in different ambient conditions. It was shown that this is actually chemical bonds forming in this between these two contacts. So we've used that to illustrate or to model an experiment that has been mentioned, which is this dynamo-acousto-elastic testing, which is basically also a resonant bar experiment, but the softening is not measured by evaluating the resonance frequency, but by evaluating actually the sound velocity across the sample. And in doing so, you can actually measure the sound velocity while this guy is oscillating. So we can measure the velocity change during each individual cycle of the low frequency resonant oscillation that we have in the lateral direction. So here is the acceleration that is measured on top, which is basically the driving at the resonance frequency of the sample. And here is the velocity that is measured across. So there's, of course, some oscillation due to this the change of strain, but there's also this decrease of the velocity when the deformation has started, and then it's kind of at a slower state, and then when the deformation stops, then it increases again. But the interesting thing here is what actually happens in the steady state oscillation. And that's shown here, the modulus as a function of the compression tension cycle. And we see that we have a decrease of the moduli when the tension is increasing, and then it increases when there's compression. But during the cycle, there's a lot of complexity, which is characterized by an increase in the modulus at the largest compression or extension, and yeah, by a certain direction. So for different strains, for different levels of the driving amplitude, we observe different shapes here. And it's, as I said, it's a fast co-seismic softening that we see, and the slow post-seismic stiffening, which I showed 2 slides before. And there's a hysteresis that is in between here. And yeah, we have the stiffening at the maximum and minimum sides of the strain. And that is an important part of the story, that the sample is actually stiffening at both extremes here. So we use this concept of the contacts forming between the different sides or the bonds forming between the different sides of a contact, but now in shear motion. So we have the modulus that depends on the number of these connections, of these bonds, and then we have a governing law for the number of these bonds that is actually depending on the strain rate. So when the contact is deformed fast, then there's a tendency for the bonds to break, so the number decreases, and when it's at rest, while when the strain rate is 0, then the contacts form again. The difference to the former model is that it's like in shear motion and not in lateral or in lateral motion. Good. So with this, and okay, there are certain time constants for the formation of these bonds, and we have a spectrum, broad spectrum of the time constants to model this log linear behavior. So with this fairly simple model, we can actually reproduce the observations rather well, and in particular, with using slip as the driving mechanism, we can reproduce the increase of the modulus at the extreme states of the deformation. So here the softening depends on the strain rate. So whenever the strain rate, no matter in which direction, is large, then we have a softening, and when the material is at rest, it is stiffening. This model has actually been used to explain a very different experiment. And that's what I would like to finish with. It is an experiment that has been done in Caspar van Week's group by Jonathan Simpson in a very controlled and very small strain environment. Because what they actually do is they try to isolate the sample from all the external influences as much as possible. So it is put in the pressure vessel, which is basically only used to insulate it from the surroundings. And then there's a laser pulse that is sent on the sample on one side. And with the Doppler vibrometer, the pulse is actually measured on the other side. And with this experiment, they actually measure the sound velocity in the sample. And the only thing that they do is they heat the whole experiment by 10 degrees, for example, and see how the velocity changes in the sample due to a response, due to the change in the temperature. So I don't know what you would expect, but the thing is, when you heat the sample from the temperature from 50 to 60 degrees, the velocity actually drops. So it drops while you're heating, and then it recovers and kind of stabilizes, but there's a long-term trend due to the environmental conditions. But then what happens when you decrease the temperature? It's not that you have an increase in the velocity, but you again have a decrease in the velocity, and you have a recovery to some steady state. So also here, you see that similar to what Manuel showed. Whenever you do something to the sample, no matter what, actually the velocity decreases here. And this is a very tiny perturbation that you put on the sample, which is just 10-degree temperature change over a few hours, and you see this effect. And now, what Johnson did, he calculated the strain that is the strain that occurs in the material due to the heterogeneity of the material and introduced by the temperature change. And he used our model to say, okay, we have internal heterogeneity, we have internal strain due to the heating, and that actually deforms the contacts. And while you are deforming these contacts, you break the bonds, you soften the material, and thereby reducing the seismic velocity. So here on top is the model, basically the reproduction of the data by that model based on the number of bonds between these contacts and which are damaged by slip rate. And they're able to reproduce these observations of the velocity changes due to temperature pretty well. So here we have the number of broken connections, broken contacts, and translate it into a velocity that kind of fit these observations pretty well. And what is important here is the slip. So it's not the distance between the contacts, but it's actually the slip, because otherwise you would not systematically have a decrease whenever you do some change independent of the sign. Okay, to summarize this, the non-classical nonlinearity originates at the grain contacts. And contacts have all the different sizes that we can imagine. So processes at the smallest level might actually govern the behavior. And slip plays an important role in these transient processes, just because these transient processes usually only have one sign. So they only go down when you damage or when you do something, and then they recover. So there's not two signs of it. Okay, thank you.